Hello, and welcome to Grade 12 Physics for our Nuclear Physics unit. Today we're going to take a look at a little bit of review of the atom and the properties of the atom. This is review of stuff starting back in grade 9, but we're going to add a little bit more to it to make sure that we understand what's going on with the atom, and in particular, the nucleus, which is what nuclear physics is about. So, here we go. I'm going to go take a look at our periodic table here. This is a wonderful website, ptable.com. And what we can actually see here is that we have all of our atoms and elements. I can choose any of these atoms, and there's many different information about them. For example, sodium here. So let's take a look at sodium and see what we've got. Now, in sodium, I know that I have protons, and I have neutrons, and I have electrons. Those are the basic components which make up any atom. Protons, neutrons, and electrons. Now, in sodium, I know that I have 11 protons. That I can find from the atomic number right here in the corner. I also know that in this case, my atomic mass is 22.99 or 23, but I have to subtract the atomic number to find the number of neutrons. So I have 23 minus 11, which means I have 12 neutrons in my standard sodium. Electrons, because this is a neutrally charged atom, I have 11 electrons, the same number as the number of protons. Now, when I'm looking at an atom, I can change the number of protons or neutrons or electrons and get something a little bit different. So to start off with, the number of protons here, if I change that number, so say I add 1 to that, what I get is I get something different. So instead of having sodium, I would move over to magnesium here. That has 12 protons, which means that this is magnesium and not sodium anymore. We get a different element. So if I change the number of protons, I get a different element. Okay? If I take a look at the electrons, this is something that you learned back in grade 10. If I change the number of electrons, so sodium typically wants to lose one electron. So let's say it loses an electron, which means that I now have sodium, but because I've lost an electron, I now have a charge of +1, which is the common ion of sodium. The sodium has a charge of +1, and this is, as I said, a different ion. So if I change the number of protons, I have a different element. If I change the number of electrons, I get a different ion and a different charge to the element, the atom. If I change the number of neutrons, well, let's say I add 1 neutron here, so I would have 13 instead of 12. What I get is I get a different isotope. So it's still sodium because I have 11 protons. It's still neutral because I have 11 electrons, but I have a heavier isotope. So I would write this as sodium instead of 23. This would be sodium 24. So this is the same thing as sodium. It's just a heavier version of it because it's a different isotope. Now, there are many different types of isotopes. If I take a look here at the periodic table, I can look at the number of reasonable or possible isotopes of these elements. So if I click on sodium, you can actually see here there are many, many different versions of sodium. Here's sodium 23, here's sodium 24, here's sodium 25. I can go all the way down to, in this case, sodium 18 here. And all the way up to sodium 37. But not all of the possible sodiums that you might think would exist. For example, we've never seen a sodium 100, or we've also seen never seen a sodium 11, which would be no neutrons. So these are the possible isotopes. If I go look at other ones, for example, hydrogen has a bunch. There's hydrogen 1, which is normal. There's hydrogen 2, which has the common name deuterium. There's hydrogen 3, which is the common name tritium. And then As we go along, there are more versions of hydrogen. Or if I look at something like, for example, palladium, I have a huge number of isotopes and it keeps going off screen, which is kind of fun. So here's what I know. Sodium can have different elements, or if I change the protons, I get a different element. Change the neutrons, I get a different isotope. Change the electrons, I get a different ion. When I'm writing this, each corner of the sodium here, there are 4 corners of this element symbol. Each of these means something important to us when we're writing these out. Now, the right-hand 2 here are used for chemistry. So, for example, I could write the charge here. And chemistry is more concerned about the charge because it's more interested in how the electrons are moving. Here, this is the number of atoms. So, for example, in a chemical formula, I might have Na2O for sodium oxide. That would be where I'd put the 2 there in that bottom right corner. For the left-hand side, physics is interested in these 2. This here is the atomic mass in the top left and the atomic number in the bottom left here. So sodium, the normal isotope of sodium is 23 and 11. So I've got 23 for my mass and and 11 for my atomic number. If I change either of those, this changes the isotope, this changes the element. Okay? This here changes the ion. So all of these are useful. We're actually going to be more interested in the left-hand side because we're looking at physics. Now, one other thing that I'd like to point out is we have a kind of a weird thing that a question should have come up in grade 9 when we learned about static electricity and learned about atoms and elements. And now we're actually going to explain that. So, as a little bit of a teaser for our next lesson, let's look at helium-4. If I have helium-4 here, you can see it has 2 protons and 2 neutrons. Now with helium-4, these 2 protons here experience an electrostatic force repelling each other. So the electrostatic force in both of these, if you remember Coulomb's law, the closer they are, the more they repel each other. They are very, very close in the nucleus of an atom, so they should repel each other. Why does this nucleus stick together? Well, it turns out that there must be some sort of opposing force that holds this nucleus together. So we have a force here, which we call the strong nuclear force. Strong nuclear force, which holds these together. And the electrostatic force of repulsion is not enough to push these apart. So for a small atom like helium here, this strong force is much stronger than the force of electrostatic repulsion. So this atom here sticks together. This strong nuclear force is sort of like the glue that holds this element, this nucleus, together. And as we go up, you may notice that the number of neutrons increases as we go up our periodic table. If I take a look at my periodic table again, let's take a look at fermium, because the numbers are easy. And fermium has 100 protons, but it has 157 neutrons. So the bigger your element gets, the bigger your atom gets, the more neutrons you need to provide or help provide that strong nuclear force so that the electrostatic repulsion from the protons repelling each other doesn't blow the atom apart. Okay? This here, where does this strong nuclear force come from and how can we calculate stuff about it is what we're going to look at in our next lesson. I hope you have a great day. Thank you very much for watching.